Uh, okay, so this is the closest group. Hello everyone, this is the closest group by Shalken, Curtis, Veronica, and me. And now we're going to give our presentations. First, I would like to introduce our motivations. I believe that no one was not familiar with earthquake. It could happen anywhere at any time. And there are in fact more than 5 million earthquakes happen every single year. That is to say, within 1 minute there are approximately 10 earthquakes occur. Though not all earthquakes are destructive, large magnitude earthquake could have a severe damage on architectures, especially ancient buildings that already built for like hundreds or thousands of years, just as the figures illustrated. Uh, this figure is a figure of Erwan Temple located in Sichuan province. It was destroyed nearly 90% in 2008 Wenchuan earthquake, and it took almost 3 years to fully repair the temple. And right over here is a comparison of Kathmandu Square before and after a large magnitude earthquake in Nepal's capital city. And the earthquake directly leads 4 temples to entirely demolish, plus the palace partially undermined. And the very right figure over here is Famen Tower, which the tower has been twice damaged by the earthquake. So preservation of cultural relics thus should take into account. And the closest that we are investigated to in this project was also very fragile and I will mention that later. We were reluctant to see the closest being damaged as a loss of human culture, and thus we decided to choose these topics. Okay, for our objectives, the goal of this research project is to understand what part of the structure will experience will be stressed the most during an earthquake, and to investigate how the colossus will behave under certain simulated excitation by using a refined 3D finite element model, while discovering the effect of soil structure interactions. Okay, now here are some interesting facts and background information about the Colossus. I bet all of you guys already have some knowledge about the Colossus legend, since Professor already talked already mentioned it in the lecture. Before crisis, there was a very strong earthquake causing the top of the northern Colossus to collapse and its lower portion to crack. The statue then began to emitted a light moaning or and whistling sound. There's one saying that the scene was made by Eos mourning for her dead son. An alternative saying is said that the sounds was the cries of the Memnon greeting his mom. A natural explanation for this phenomenon has also been suggested, which I personally believe is the most reasonable one, though I'm not familiar with the mechanism. It has been suggested that it is due to the increased temperature at the morning, the dew inside the porous rock starts to evaporate and causing the statue to sink. The Colossus also have a very long history. It is about 3,500 years old. That is much more older than the Pisa and the Giotto Bridge. Considering the closest significance, it is the most important statue in Egypt after the Giza Sphinx. And the original function of the Memnon Colossus was actually to guard the entrance to Amenhotep III's memorial temple. For location, as we all know that Colossus was located at Luxor, Upper Egypt, it was also situated right at the Mediterranean seismic zone, where frequently experience earthquake and annual flooding from the Nile River. Glass refers to the statue's fragility. The South Colossus arm was broke, and there are also lots of fractures occur not only at the body of the Colossus, but also the base of the structure. So that's much about it. And now let's welcome Curtis to introduce the methodology part.
Can you see my screen?
Yeah.
Okay, the second part is the methodology. In this research topic, we mainly focus on the dynamic response of the Southern Memnon Colossus. First, here's the mind map is the overview of the methodology. We separate the whole process into three parts: a modeling and the properties, full method, and MSUP method, which is known as the mode superposition method. The full method contains a nonlinear analysis of the statue-only model in the transition system, and the MSUP method contains model analysis as the prerequisite of the transition system and the harmonic response analysis. And the parametric studies were applied in both studies. And then would be the modeling part. The modeling part is the process of building finer models based on Werdell's model. The picture here shows the Werdell's model are made up of coarse cuboid and overestimate the volume of the real one. After I observed the photograph of the real closely, parts of the statue are removed. You can see the red rectangle here. The right arms were removed, however, the left arm remained. So I built a similar model to simulate the real one. The right arm are removed, and the left one remains. Remains. And you can see the left shoulder here is a little bit wider than the right one. And two models are built in order to make a comparison and to see the soil interaction on the statue with the matching size of 1000 millimeter. The statue calculation has its accuracy. And the statue soil combined model is divided into three parts, with the upper statue remain the same. The lower part is composed of 6m thick silt layer and the 5m thick limestone layer. And the physical property of all material are in the table here. There's Young's modulus, Poisson's ratio, and the mass density. The contact between the silt layer and the limestone layer, you can see difference in the color, are considered as bonded. Due to the limitation of the ANSYS academic, the soil foundation is built as a playground-shaped one with a meshing size of 2500 millimeter. Next part is the model analysis. Model analysis are used as a prerequisite to identify the natural mode of vibration. Each mode in the model analysis refers to natural vibration characteristics of the mechanical structure, and each mode has its own specific natural frequency. The model analysis aims to find the natural frequencies, which are the inherent properties of the structure. No load will be applied in the model analysis process. Correspondingly, boundary conditions, like the fixed support in both cases, are applied at the bottom of the statue and the soil foundation. And here is the first 6 mode of the vibration. The next part will be the transition analysis in the MSUP system. Transition analysis contains a time domain, and we set the step and time for 2 seconds, and the maximum substeps for 100 and minimum for 10. For the boundary condition, we add a fixed support at the base, and as well as the frictionless support for the statue soil combined model, we add at the side of the soil to limit the freedom of 2 directions. And we're using the sinusoidal wave to simulate the real earthquake motion, and the fundamental wave are here as shown, A sine pi t. And we add the base excitation at the bottom of the statue. After that, we apply the parametric study to change the amplitude and frequency, as well as the direction, to see if there is any linear or nonlinear relationship. Next part, you can see here it is shown the wave of the direction. The next part would be harmonic response analysis. Different from the transient analysis, it contains a frequency domain, and for the boundary condition, also the fixed port at the base. And the minimum frequency just covers the first mode of the frequency, and the maximum frequency minus the minimum frequency is 1.5 times smaller than the interval of model analysis. And consider about our model is a compact one, so we only consider the first two modes of the model. So we separate the from the 15 to 35 to 30 intervals. And in order to find the resonance effect, we set those intervals to approximate the real frequency. And also the base excitation applied at the base of the statue. And finally, the frequency response will carry out to see the total deformation or stress given a frequency domain. And the final part is the transient analysis in the full system. In this analysis, we consider the nonlinear factor and also the elastic support between the statue and the base with the stiffness of 100 Newton per cubic millimeter. With the frictional coefficient of 0.3 and the force displacement at the bottom as the excitation with wave sine pi t, sine 2 pi t, and tan sine pi t. The analysis settings contains a total time domain of 2 seconds, only one time steps with initial and a maximum substeps of 200, and minimum substeps of 20. And then at the end, we will use the force convergence in the solution output to check whether the problem would converge. And next part would be the result and the conclusion by Xiaokun.
Okay, so this is the results and conclusion part. For this model part, I will show the first 6 modes of the statue-only structure and the comparison between the statue-zone combined structure. And this guy here, it is a statue representing the statue-only structure. And this guy here is like a brick, so it's representing the statue and soil combined structure. And in the transient analysis here, we will show the results when we vary the statue's frequency, amplitude, and direction. Also, we will do the same thing to the statue-soil combined structure and the comparison between the statue-only and the statue-soil structure. As for the harmonic response part, we want to see the response when the frequency changes, as well as whether it will blow up when the frequency of displacement function approaches the natural frequency. So the last part is the transient analysis. This part we will show the solution convergence and the sliding phenomena, also the comparison between full and MSUP system. So for this statue-only condition, we keep the first 6 modes. The first 3 modes, as you can see, is the banded ones, and the 4th and 5th ones are twisted one, and the 6th one are stretched one. Each of them corresponds a natural frequency. And this is the animation of the first modes of the statue, and also the first modes of the statue soul combined. You can see that they are pretty much alike, both banded. And this is the 5th mode of the statue and the statue soul. They are both twisted. And this is the 6th mode of the statue and the statue soul combined. They're both stretched. So as for the transient part, this table illustrates the maximum deformation and equivalent stress trend when changing the frequency here from 0.512 and 16.51 Hertz, which is the first natural frequency in particular. And this diagram turns out that during the domain of 0.5 Hertz to 2 Hertz, as the function's frequency increases, the total deformation and equivalent stress of the closure reached in a linear-like trend. And though total deformation and equivalent stress obtained from 16.851 Hertz did not confirm with the slope before, it shows that the closure did not experience a blow-up as the frequency of the function approaches the natural frequency of the statue in this transient analysis. And this is the deformation contour when applying sin pi t to the structure. And this is the animation. So besides, we changed the amplitude of the displacement function from 1 to 100. The magnitude of stress and deformation on the closure are strictly proportional to the amplitude of displacement function. We also applied different orientations with the function remain the same, including the north-south direction, east-west direction, and the north-west southeast direction. In NS and EW direction, which is north-south and east-west direction, the two total deformation are nearly the same, around 1, while the total deformation of NWSE direction is around square root 2, which is within our anticipation. When it comes to stress, the EW direction is the largest among them. Same as we did in previous analysis, in statue soil analysis, first we select the frequency, which is 0.51 and 2 Hertz. But this time, the acquired results are very different. The total deformation represents a linear decrement from 0.5 to 1 Hertz, followed by a horizontal line, which is 1 Hertz to 2 Hertz. We are so unconvinced of the strange trend, so more frequency points are taken into consideration, which is 0.25, 0.75, and 8. And it turns out that from 0.25 to 0.75, the total deformation remain a horizontal line. Then with a descending period, and then continued with a horizontal line. And as for the stress, since they're too close to 0, the trending analysis seems relatively redundant. We just consider them as 0. And this is the animation of the statue-soil combination. So when we use different amplitude in statue-soil combination case, the stress and deformation were also linear proportional to the amplitude. And once again, we measured in 3 directions. The maximum deformation on the structure occurs when the seismic wave was applied at EW direction, while the most moderate in NS direction. Note that when applying the EW direction function, the total deformation was surprisingly greater than 1, which is out of the anticipation we had earlier. And if we compare the data obtained with and without the soil foundation, we discover several conclusions. Firstly, the total deformation and equivalent stress value of the statue, identically displacement function at the base were dramatically smaller when considered soil as a part of the FE model. The deformation with soil was approximately 1/5 of the model without soil. Thanks to the contribution of the soil, the stress in statue soil combined model could be reduced to nearly 0 in all 3 directions, in all 3 cases, frequency, amplitude, and directions. And thirdly, and secondly, all results indicated that the total deformation and equivalent stress was linear proportional with the amplitude of the seismic wave strictly. And thirdly, the deformation and the stress in statue soil combined model were proportional with each other on a particular direction, while no obvious relationship was observed between those quantities in statue-only model. In both cases, the minimum stress occurred at NS direction, while the maximum the maximum stress appeared at EW direction. Besides, it is out of anticipation that when soil was considered, the deformation in EW direction was even 4.7 times larger than the statue-only model. We were so confused by it, so we made another circle soil model. The results changed accordingly. So we discovered the size and the shape of the soil may affect the results. And as in this harmonic response part, as the results, as the graph illustrates, when the frequency was 17.67 Hertz, which is close to the second model frequency, which is 7644 Hertz, the maximum of deformation approaches to 118. However, when the frequency increases to this period, the maximum of deformation its deformation dropped to an ordinary level. And then you can just imagine if it comes across another natural frequency, it will just rise up again like waves. And then the excitation frequency was set 16.851 Hertz, which is the first model frequency, which is exactly its maximum total deformation was approximately over 58,000. We could therefore conclude that the renaissance could result in a significant level of deformation and could lead to serious damage to the structure in this harmonic analysis. Then we observed sliding. Then the next part is the transient analysis using full mode method. These results are very easy to diverge, so we use the forced convergence in the solution output to check if the problems diverge. In this picture, those green vertical lines and the absence of bisections clearly illustrates that the problem is converged. Then we observe the sliding phenomenon when the displacement equal to sine 2 pi t and 10 sine pi t. We can conclude that under a certain value, like increasing the amplitude or frequency, the statue will start sliding and lead further damage to the whole structure. The picture here is the auto scale in order to see the sliding phenomena. Actually, it slides much less than showing on the graph because it is auto scale. And this is the animation of the 3D sliding. And then there will be a comparison between the full and MSUP results. We compare the results when the displacement wave is sine pi t. And we could see that the shape of the maximum total deformation, which is the orange color one, are nearly the same, and their values, maximum values are nearly the same, both around 1. However, the discrepancy of the minimum and the average deformation are also obvious. And we anticipate that because the full method provides a sliding condition, and this question could be focused in future study. That's all. And I will move to Queenie.
Okay, the next part of our presentation is a summary and conclusion. And for the transient analysis, the first point we found that is the total deformation and equivalent stress values of the stature are dramatically smaller when considering the soil as a part of the finite element model. And the second point is that the deformation with soil was approximately 1/5 of the value from the model without soil, and the stress of soil stature model could be reduced to nearly 0. And the first two points can be shown in the first two table, and the third point is that the amplitude of the seismic wave is linearly proportionate with the total deformation and equivalent stress. And this can be shown in the third chart. And the last one is the deformation and stress and stature soil combined model were proportionate with each other on a particular direction. And we also found that the minimum stress always occurred at north to south direction, and the maximum equivalent stress appeared in east to west direction. And for the harmonic response analysis, we found that when the frequency increases, the directional deformation drops to an ordinary level, as is shown in this picture. And we can conclude that the resonance, when we apply frequency close to the model frequency, can result in a significant level of deformation and lead to serious damage to the structure. And for the transient analysis using full method, we found that when the wave function comes to 10 times sine pi t and sine 2 pi t, the statue started sliding at the base, just like the right one picture shown. And the next part is our recommendation for future work. First, we can solve nonlinear problem, because in this research, we considered some situations were linear, which can be too idealistic for the real situation. And we also can use a different shape and size of soil foundation, because this time the soil foundation, we use the shape of it is just like a playground, and maybe we can try a circular foundation if we have more time. And we also can apply a more realistic seismic motion with a more appropriate step time and boundary conditions, because a real seismic wave is not like sinusoidal function. And we also can develop a method to distinguish under what deformation the statue will topple. And the last point is we can find some repairing methods for the Colossus according to the collective response to avoid the collapse to the Colossus when it experiences an earthquake and not damaging the surface and structure of the whole stature at the same time. And the final part of our presentation is an acknowledgement, for we received a lot of technical support and theoretical support by Professor Borja, T.A. Blair, and Cindy, and we quite appreciate for that. And that's all. Thank you.
Thank you.
Very nice. All three presentations, very impressive. I have a couple of comments regarding the problem, not the presentation, but the problem itself. There is a thing called site amplification. So what it means is that depending on the material properties of the soil, if you apply a certain earthquake excitation at the base, you could either amplify the motion to the ground or de-amplify it. So it's not always the case that the motion will be de-amplified. It really depends on the combination of the characteristics of the earthquake motion and also the material properties of the sediment. So in some combinations, maybe your deformation at the statue will change. Now, if you add the statue in there, the modal characteristics of the combined structure will generally change. So it is not sufficient to do a site amplification analysis without the structure. So what the group has tackled is a very, very complicated problem. Now, the second point that I'd like to make has to do with the fact that when the structure undergoes seismic excitation, then it vibrates, and there are waves generated that go away from the structure. And then they move toward the boundaries of your finite element mesh. Now, in general, those boundaries are going to reflect the waves. And those reflected waves going back again to the structure is a fake wave, because in general, it is supposed to disperse away towards infinity. So a more complete analysis would be to introduce what is called absorbing boundaries. And those absorbing boundaries will capture the propagating outward waves so they don't bounce back to the structure. Otherwise, your response, structural response, will be polluted by the bounced waves, the reflecting waves. Other than that, I think the presentation was very nice. One question was, is there any reason for the choice of the fish skeleton?
No, I just think it's very like fancy, and it also illustrates clearly, so I choose it. It's like
I thought it was because you are the statue was next to the River Nile that you were going fishing.
yeah, it also corresponds with the theme.
Okay,
because we do the
go ahead.
because we do the parts separately, so we have to confirm a certain thing. It's the same thing.
So I wonder
Thanks,
if you could,
thank you for explaining.
Yeah.
The fake wave and the surprisingly 4.7 times.
Anyone else? Anyone else has a question for the group? Well, congratulations. I feel like giving you all A's.
Yes,
So now
finally, we made the full analysis.
No, thank you. I got your reports too, and they look awesome. So the next thing we need to talk about, perhaps, what are we going to do tomorrow? I heard it's going to be talent show from Cindy.
Okay, I will.
Okay, great. So anything else? I don't see the face of Selena. I was going to take a picture of the class.
I'm here. Ooh.
Okay, so 1, 2, ready, smile. One more. Oh. 1, 2, ready, smile. Okay, I will see you guys tomorrow.
Thank you, Professor.
Everyone.
See ya.
Thank you. Bye bye.
Bye bye.